Okay. So Monday we finished off heterogeneous nucleation, right? And now we have to talk about today the growth of pure substances, right? Most of the time we're going to be uh, most of the time when we're talking about solidification of pure substances, we're really talking about metals, right? But the important thing to realize here is that if you're not a metallurgist, right, everything that we talk about here actually applies to solid vapor processing too, right? So chemical vapor deposition or physical vapor deposition, um, in terms of semiconductor device manufacturing, right? Everything we talk about growth here applies, right? With the exception of dendrites. But these ideas of interfaces and interface mediated growth, this is all completely relevant to there, right? It also has to do with the growth of polymer crystals, right? But it's a little that's a little different, and we'll have sort of our own separate lecture on polymer processing, because what's going on in the macromolecule mix is a little different, but the fundamentals are basically there, right? So first, I want to just take a couple minutes and talk about the structure of solid liquid interfaces, right? And there's this question about what is the structure of an interface is really actually a deep question, right? Because we tend to think about an interface as being something between two things, right? It's really easy to say, well, the interface is the boundary between the solid and the liquid, right? Or in terms of our solid transformations, it's the interface between one solid phase and another solid phase. But we normally don't stop and think that the interface itself actually has a structure, right? And we really should, because we talk a lot about our favorite Gibbs-Thompson rule, right? If we say that an interface has a surface tension, well, that means it has a different stiffness. It has different properties than either phases. And as material scientists, we know that structure is what controls the property. So therefore, the structure of the interface controls the properties of the interface. But what does it actually mean for an interface to have structure? And we're going to touch on that just a little bit today. It'll make more, I guess it'll be more of a concrete concept when we talk about solid-solid interfaces. But so for liquids at the first level, we can think about some materials have very flat, planar solid liquid interfaces. Some materials have sort of these rough or diffuse solid liquid interfaces, right? And this really controls a lot of properties about the solidification, right? So if you think about it, this rough or diffuse interface, it's really easy for an atom to jump on anywhere to grow this forward. But if I have this atomically flat interface, right, intuitively we can say, oh, this is really flat. So that means this is probably a higher interfacial energy. And so if I put one atom here, now I've added quite a significant protrusion to this flat planar interface, this perfectly flat interface. So that means adding to this and making it grow can really alter the system. So I can expect potentially that the growth rates of flat interfaces versus diffuse interfaces are going to be quite different. And it turns out that there's some really nice solid state physics that we're going to really gloss over, right? That says the atomic arrangement of these interfaces is really going to be dependent by a combination of the melting temperature and the latent heat of fusion of the material, right? So how high the temperature is and the heat released. So another way of saying that is that the atomic arrangement is going to be directly related to the entropy of fusion, right? And so materials with a very high entropy of fusion are going to tend to take a planar interface, right? Which means things like ceramics, right? So, or metals or alloys that form an ordered structure, right? The greater the change in number of atomic configurations between the liquid, which is going to be disordered, and the solid, the more likely we are to form a planar interface, right? So another way of saying that is if this ratio is greater than about 4R, we're going to have a smooth solid liquid interface. If it's lower, like for metals, where this ratio is about equal to R, it means we're going to have a rough interface. And if we consider an interface at equilibrium, at the equilibrium melting temperature, right? We can sort of see where this interfacial energy actually comes from by looking at, we know that their interface has an increase in Gibbs free energy, right? But at equilibrium, we know that the Gibbs free energy of the solid phase and the liquid phase has to be equal, right? But the enthalpy of the solid is less than the liquid, and the entropy of the liquid is more negative than that of the solid, right? So the TS term, I mean, the liquid obviously has a greater entropy, but because in the Gibbs free energy we have the negative term here. When we add those together, they don't exactly compensate at the interface. It's really interesting that at the equilibrium temperature, is where the change in enthalpy and the change in temperature times the change in entropy is equal, right? That's just maybe another way to think about it. But when we're at the interface, we have this excess Gibbs free energy that is our interfacial energy, right? So that what this tells you is that even at equilibrium, the two phases are in equilibrium with each other, but neither one is actually in equilibrium with the interface. If the interface has its own structure, right, and its own properties, we can think of the interface itself. Some people, some researchers like to think of the interface as another phase, which means that even at the equilibrium phase transformation temperatures, the interface is not in equilibrium with either the solid or the liquid, right? And that is another way of thinking about what's the origin of this Gibbs-Thompson effect, right? We have an increase in chemical potential in the interface region because we're not in equilibrium with the surroundings. So thermodynamics, right? It's confusing. It's hard to be intuitive, but at least it's self-consistent, right? So no matter how we look at all of these different problems, our thermodynamics works out for us. All right. Okay. So this interfacial energy can have a very strong effect on the solidification microstructure, right? And so here we see these are both dendrites. So these bright areas here are actually the first to solidify, and then this material in between is the eutectic phase. We'll talk about this in detail starting Friday when we talk about solidification of mixtures and alloys. But which one of these has a higher interfacial energy? A or B? Any idea? You can make a consistent argument, I would say, at least in my mind, for either one, but only one of them is correct.
I'm going to make an argument if that's okay.
Yeah, go
You
ahead.
know me. First off, do you recognize who this is by my voice by this point?
Yeah, Kevin, it's hard not to recognize. If I ever saw you in person, I wouldn't recognize you until you spoke, though. I still am having a hard time getting everyone's face from the pictures you sent.
All right. Well, I'm going to go with B because the clusters it's forming are larger and it has a smaller curvature.
Okay, so the smaller curvature is definitely part of it. So B does have the higher relative interfacial energy, right? So let me make an argument for why you would think A, right? Because if you calculate the surface area per volume of the particles, right? The one that's going to minimize the amount of interface is a sphere, right? So you would expect the minimum interfacial energy to be right, the one that minimizes the surface to volume ratio, and therefore right, that's what you would expect, except we have to remember that these are crystals and we have an anisotropy, right? So what really happens is when you have a high interfacial energy material, the system can lower the energy by having preferential growth along the crystallographic planes, the crystallographic directions that have the lowest interfacial energy, right? So when you have a low interfacial energy, the anisotropy of your system isn't much, right? And you can grow to a nice sphere, right? The system can conform to, it's going to want to, let me start this over. The configuration that minimizes the overall free energy of the system is the one that minimizes the total surface area of the interface. Whereas in higher misfit, higher energy interfaces, you have to contend with the anisotropy of your system, right? So you tend to make these angular type interfaces, right? And as Kevin pointed out, it also minimizes the curvature, except at the corners, right? Okay, so we talked about nucleation. Now we've got a stable cluster, right? We know a little bit about what the interfacial structure is. Now, how do they grow, right? We already said that these interfaces can be atomistically smooth or diffuse, right? And whether or not we have a smooth interface or a rough interface we're going to grow or move the interfaces in our system by different mechanisms, right? So our smooth interfaces grow by a lateral growth process, which occurs by the movement of ledges of atoms or molecules, right? More on that in the next slides. And rough interfaces are going to grow by a continuous growth process. And we also have to keep in mind that depending on what the thermal gradients in our system, we can have growth instabilities that can occur, and that leads to dendritic growth, right? So let's just talk about continuous growth for a minute, right? So we know if we have an atom in our liquid and our atom in our solid, right? We know it's a thermally activated process. We have an activation energy that has to be overcome to move the atom from one position to the other. It should make sense that this activation energy has something to do with how easy diffusion occurs in the liquid, right? Since we're moving from the liquid to the solid. And that, notice that our actual change in free energy for the atom, right, is quite small. So that's the solidification, even though it's going to be heavily biased towards liquid moving, atoms or molecules going from the liquid to the solid, we still have the reverse process occurring, right? We do have atoms jumping off the solid and going back into the liquid. It just happens that this forward process is happening faster than the reverse, so that the net movement is for the formation of solid, right? Our driving force here, this change here, is going to be sort of a function of the undercooling, right? And so why did I say this change is relatively small? Right? We just spent all this time talking about nucleation, where we had really large, said we need large undercoolings to nucleate, right? Well, that was the homogeneous case, right? Most of the time we're nucleating heterogeneously, where we need a much smaller undercooling. Therefore, the driving force for solidification is going to be less, right? And we know that for metals, in particular, the growth process happens very fast, even at relatively low undercoolings, right? So growth can happen at undercooling at temperatures very close to the melting temperature without any appreciable undercooling needed. Whereas for nucleation, we need a much greater undercooling. So if you think about this, if we're at very small undercoolings, we're going to typically have a much larger grain structure, right? In a metal, we're going to have a much larger grain size because nucleation can be difficult with a small undercooling, but growth is easy. So a small number of nuclei are going to mean a large grains. If we have a larger undercooling where nucleation is easier, or we have really easy heterogeneous nucleation and we have lots of nuclei, that means we're going to have lots of very small grains, lots of very small crystallites. Right? So that's an important concept that's going to come back. It's not really in this slide deck, but it's related to things we're going to talk about in the future. Right? The really important thing is that this process is very fast, right? The velocity of the growth is going to be directly proportional to our undercooling, but K1 is a very large constant, right, that describes boundary mobility in K1 is going to scale with the diffusion coefficient for the liquid, which is quite high. And so essentially we can say that the velocity of the interface in a metal is going to be approximately equal to the rate of heat conduction in the metal, right? Which in your from transport, you guys know or will know that this is very quick, right? Metals are excellent conductors of heat, right? Okay, so essentially, this is the continuous growth process. Atoms can just jump on and leave anywhere, right? That's why the interface gets rough. Lateral growth, if we think about this schematically. So now let's pretend this is an ionic ceramic, right? If we have a atomically flat interface and we put one arriving atom onto this interface, right? Essentially, if we think we have a coordination number of 4, right? So each cation surrounded by 4 anions and vice versa, right? We have one missing. So we have 3 on this surface. We have 3 bonds with 1 missing. If we add this atom here, we make the one directly underneath it happy, or make this ion arrive here. We make the ion underneath it happy. But then we have 5 unhappy bonds, right? So that means that putting a new ion on this atomically flat interfaces is equivalent to creating 4 broken bonds, right? So since the interfacial energy is high, that means that this, there's a penalty associated with this, an energy penalty that we have to pay to create a new layer. If we have a ledge or a step and we put a new atom here, we can work through the same logic and see that we only increase by 2. But if we're growing this kink out, it doesn't change our number of broken bonds at all, right? So creating a new layer is very hard. Creating a new kink on a ledge is not quite as hard. And then growing that ledge by this kink is easy, right? So now the question is, how can we create these ledges, right? We know this configuration here is highly unstable, right? This atom is in such an energy unfavorable state that it's just going to hop back into the liquid, right? Sure, you're going to have atoms or ions that do this all the time, but they were much happier in the liquid surrounded by all their friends than they are here all by themselves, right? So there's a couple different ways we can grow a ledge, right? So we sort of have this repeated nucleation where we nucleate a cluster here, where we have a whole cluster that comes down at once. We could have spiral growth, or there's twin interface mediated processes that we're not really going to discuss because they're sort of special cases and the physics doesn't relate back to anything. Spiral growth is kind of the easiest to get a handle on, right? So imagine we have a screw dislocation that intersects the surface, right? So this is like, now this plane here becomes like a parking ramp, right? I can just drive around, right? Which means I have a built-in ledge now whenever I have a screw dislocation that intersects a surface. So it's really easy now to just grow onto this existing ledge and just keep spiraling around and around and around and around, right? Now the only real tricky part to consider, and we don't need to worry about the exact energetics of this, is what about when we grow the grow this crystal near this dislocation core, right? Because the atomic structure in the dislocation core is not really well defined, calculating the energy of this is quite difficult, right? So when you do your structure class, you'll talk about core energies of dislocations. I don't want to get into that here, but it's a really an interesting topic. But you can see how the spiral growth of a crystal can occur, right? It's not as fast as continuous growth. At small undercoolings, it's a constant times the undercooling squared, right? So if the undercooling is small and this K3 constant is much smaller than the constant for continuous growth, you end up with something that's not as fast, right? Keep in mind, though, this velocity equation predicts that at large undercoolings, this will rapidly overtake the growth rate for continuous growth, right? This model is only, this model for growth rate is only valid for small undercoolings, right? What happens is that at larger undercoolings, it asymptotically approaches the growth rate for continuous growth. It doesn't overcome it. To nucleate on a surface, right, we can also have surface nucleation, right? So I guess before we go on, a natural question to ask is how common are these screw dislocations that intersect a surface, right? Well, it turns out these are actually fairly common, right? In epitaxial growth and in device fabrication, for those of you that are interested in functional materials, right? You can imagine if you're growing something on a substrate, right? So you have a silicon wafer, and I'm growing some other semiconductor, right? Let's say like a 3,5 type semiconductor on a silicon wafer, right? The mismatch, say, between silicon and germanium, they're not the same atomic radius. So there is a mismatch in size or an elastic strain. So if I only have one or two atomic layers, I can accommodate that strain by either squishing or dilating my the substance that I'm growing. Right, it's not so hard to stretch a thin film, but as that gets thicker, the stress on that interface becomes greater and greater, and so one way to accommodate that mismatch of lattice in semiconductor devices is to nucleate threading dislocations that run perpendicular to your surface through the thickness of the crystal that you're growing, right? So while talking about that in detail isn't super relevant for what we want to do, it's a little off topic, but just keep in mind that the spiral growth mechanism, this happens all the time, especially in the fabrication of functional materials and devices, because of the existence of threading dislocations, right? So this is a ubiquitous kind of thing. And actually, the surface nucleation is a little, probably run into it a little less often. This tends to happen when you have like solute processing of ceramics, like sol gel type reactions and things like that. But anyway, we already know that a single atom joining onto this surface is unstable, right? But we know from nucleation theory that we can make a stable nucleus if we exceed some critical radius, right? So obviously nucleating a small cluster on an already existing surface is different than nucleating a cluster, a spherical cluster, homogeneously in the middle of a liquid, right? So the radius here, the critical radius to nucleate one of these growth clusters is different than the critical radius for homogeneous or heterogeneous nucleation of the solid directly from the liquid. But the concept is still exactly the same. There's going to be some stable disk size that if we nucleate this disk, then it's going to stay stable. And then once nucleated, this disk can rapidly grow by ledge mechanisms. There's another subtlety here because in reality, this schematically, we show this disk as being round, right? But this disk is actually atomistically rough, right? Because you can think of it like a pixelated thing, right? You can't put atoms in between the lattice positions, right? Right. You have a pixel size, like if you were doing raster computer graphics or something, or bitmap type graphics. You have a pixel size that's equivalent to your atomic size or ionic radius. So what we have here is we have this disk here that's going to nucleate. It's going to then grow pretty fast relative to how hard it is to nucleate here. So what you end up with is an incubation time between layers, right? So you have a step growth type behavior. We nucleate, we grow. We've grown 1 atomic distance high. Now we have to wait a little bit of time for the next nucleation event to happen, right? So the growth here for surface nucleation isn't as smooth as it is for others. And because we have to overcome the energy difference between these two states, our growth is going to be given by Boltzmann statistics, just like for nucleation theory. So what does that mean? Oh, I left out the image. There's an image in your reading that shows... Yeah, Sean's got a question.
I'm sorry, this might be a bit too late, but a few slides ago, you said that the equation would be used for small undercooling. What exactly do you find a small amount of undercooling as?
It's not necessarily an easy question, but sort of in practice, right, this is a couple of degrees to say maybe 10 degrees Kelvin or so, right? So a small fraction of the melting temperature, right? So we're talking about things happening above, say, 0.95 TM.
Okay, thank you.
Right, so approximately, right? But right, so what really happens is this velocity curve approaches asymptotically to the continuous growth curves, right? And I accidentally left out a slide that showed that, right? Basically, it just showed that at very large undercoolings, all three of these, the velocity of all three of these mechanisms approaches each other, right? But at lower undercoolings, surface nucleation is the slowest, spiral growth is faster, and then continuous growth is the fastest, right? So cool. Thanks for if you have a question that I miss in the chat, right, just hit the hand raise thing because I got a nice big notification on the screen. So that's good. So for heat, the next thing we're going to talk about is thermal dendrites, right? Or how instability Kevin just tested it out. So what's up, Kevin?
Well, I was confused on this from the reading. When they say a small undercooling, do they mean a smaller number or like a larger negative number?
Think about it in terms of fraction of the melting temperature, right? So it's relative to the melting temperature, but also needs to consider the heat of fusion, right? So you can just think of a rule of thumb as a small undercooling is like 99 or 98%, maybe down as low as 95% of the melting temperature.
So a larger undercooling is further away from the melting temperature.
Large undercooling means smaller absolute temperature farther away from the melting temperature.
Got it. Thank you.
Right, and that's I'm glad you asked that, because it's something I tried to keep clear, but it's something I think a lot of people might potentially get confused about. Right, it seems weird to talk about, yeah, a large temperature, large related to temperature, to actually mean smaller absolute temperature, but that's the language we have. There's lots of confusing sort of counterintuitive language that comes up when you talk about the strengthening of metals and alloys. The common terminology is strong and weak obstacles for dislocation motion, or hard and soft obstacles. But then when you talk about the mechanical properties, you come up with weird things like weak precipitates are strong obstacles, or soft precipitates are hard obstacles, right? Just because of the weird way language gets combined. So it's the same way. Large undercoolings are low temperatures. Okay. So if we think about a atomically rough interface, right? So we have all these little sort of tiny little protrusions that are on the surface, right? Because we don't have this nice flat interface. We already said the solidification rate is going to be determined by heat conduction. And so our interface overall moves at a velocity that's determined by how fast the latent heat of solidification is going to be conducted away from that interface, right? And the question we have when we think about growth instabilities like dendrites is, what is stopping one of those tiny little protrusions from growing out into the liquid faster than the surrounding neighborhood, right? And creating essentially like a needle that's growing out, right? Why does the whole interface move forward with a constant velocity? And obviously we wouldn't be talking about it if it didn't happen, right? So there are definite cases where we can get dendritic growth, and we do have a protrusion that grows away like a needle, right? And it's important to realize that this conduction of latent heat away from the solidifying interface can occur either through the solid or the liquid, right? Which means it all depends on the direction of our temperature gradient, right? If we are if we're solidifying into a superheated liquid, right? So say we have a chilled mold, right? What that means is, since heat conduction through the liquid isn't instantaneous, right? It's fast, but it's not instantaneous. It means we reach a critical nucleation temperature at the mold wall, before we have, and the temperature of our liquid is still high, right? So now our interface is growing into a superheated liquid, which means that our direction of thermal conductivity is our solid is cooler than our liquid, so the direction of heat flow is going to be through the solid. It's the exact opposite if we're solidifying into a supercooled liquid, right? So if we came down and we nucleated, say, heterogeneously from particles in our melt, we have an undercooling in our liquid. So that means our solid is going to be essentially at the melting temperature. Our liquid's going to be cooler. So that means the heat flow is going from the solid into the liquid, right? So we have to consider what happens in both of these cases. And one of them leads to unstable growth, right? So, but we need to start out by talking about our heat flow. So in the reading, Porter and Easterling use a prime, an apostrophe to indicate the gradient, the derivative. I think it makes a lot more sense if you actually put the nablas in there, right? So we have our heat conduction times our gradient of our temperature in the solid, right, has to equal to our conductivity coefficient times our heat conduction in the liquid plus the heat generated, the generation of the heat of fusion, right? And that's going to be proportional to the velocity of the interface, right? And because we have an undercooling, right? We're talking about a non-equilibrium process here, right? Always keep that in mind. Okay, so if we're in the case where we have heat extraction through the solid, right? Meaning we're going into a superheated liquid, right? If this is a planar interface, our our temperature at the interface is exactly the melting temperature, the equilibrium melting temperature, right? We're chilled. We have a chilled mold back here. We have some equilibrium temperature of the liquid that's far away, right? And in this case, we're going to be stable. This is going to lead to stable growth where this interface moves forward and stays flat, right? Not necessarily atomically flat, right? Right? This can still be a diffuse interface, but macroscopically, it's going to remain planar. Okay? So we can imagine if we form a little protrusion like this. And for the sake of this argument, let's pretend that the radius of this protrusion is relatively large so we can ignore Gibbs-Thompson for right now. Right? We'll take Gibbs-Thompson into account when we actually consider dendrite growth. But for now, let's ignore that. Okay? The interface is at the melting temperature everywhere. If this protrusion grows out, right, it means that we're now going to have a steeper temperature gradient in this portion of the liquid and a shallower temperature gradient in this portion of the solid, right? Because the mold wall, our boundary conditions at the wall are fixed, and we have a constant temperature in this sort of the center of the liquid, right? So we have a steeper gradient here, a shallower gradient here relative to the areas of the interface that it's planar, right? That means that more heat is going to flow into the solid here, and our growth velocity is going to change, is going to decrease here, and the rest of this interface will catch up, right? Right? So think about that. Oh yeah, so the there's a couple questions that I didn't see before. So why is epitaxy different than heterogeneous nucleation? It's slightly different because in heterogeneous nucleation, you're nucleating that disk on a different material, right? So you have to consider the surface energy between the energy of the interface between the solid that you're forming and your substrate that you're nucleating on, right? So your first layer of epitaxy is essentially heterogeneous nucleation. It's the same. But your subsequent layers, it's easier to nucleate on the same material than it is to nucleate on a different substance. Or it could be more difficult, right? Depending on what those surface energies are, right? So that's the primary difference between heterogeneous nucleation and epitaxy. But other than that, you're right. It's exactly the same, right? So everything we talked about for heterogeneous nucleation also applies to epitaxy and vapor processing. And that image that I was talking about earlier that shows the asymptotic curves, that is right in the reading. Okay, so we'll talk about this based on the words you chose. So maybe I need to be more careful with the words I choose then. So I want to be careful because I'm definitely not an expert on processing by epitaxy, right? I mean, I'm a metallurgist, so that means I'm kind of dumb when it comes to functional materials. But for the sake of the level of the argument that I want to make, essentially, yes, right? You need to nucleate each layer when you're doing epitaxial growth, except in the case where you have threading dislocations, right? But you're still growing layer by layer epitaxially. So the exact specifics are going to depend whether you're in the first couple layers or whether you're in a thicker regime, right? If you're in the first couple layers, yeah, you're going to have to nucleate each layer individually until you have a sufficient threading dislocations, right? I'm sure if Professor Grassman heard me say that, I would he'd have some stern words about my what I'm saying, right? Because I'm sure the physics in there is actually probably slightly different. And I will actually see if he has any a couple quick slides he can give me that I can share with you guys to make it a little clearer. But I wanted to talk about that processing sort of a little bit later on. I sort of brought it in as a divergence, right? So hopefully that answered your question in the interim, and then we'll have a longer discussion on it. So I'm a couple minutes over, so we're going to stop here. We'll pick it back up on Friday here and talk about the remainder of dendrites and then dendritic growth, and we'll get started with alloy solidification. But there's some sort of kind of non-intuitive concepts to get through here. Why does this interface velocity slow when my thermal gradients change? Right, so we'll have to talk about that a little bit because that's the easier case, right? When we talk about where we get these runaway instabilities, we have to, it's the other way around. Okay, so we'll see everyone Friday. It looks like the class is pretty split on the due dates. So what I'll do is we'll just make them be due later in the week. Instead of being due on Monday, we'll make them due later. And I guess what it does is it puts a little bit of onus on you guys to get to the office hours. If you have some problems, right? I have my office hours today, just as a reminder. So if you have questions on the next homework assignment, feel free to stop on by. Okay, take care, everybody.